you're constructing a new understanding of division. You may have had only a fair sharing understanding where you would read this just as 8 divided by 4. Maybe think of it as 8 divided into 4 groups. But that forced you to know how many things were going to be in each group. That understanding didn't transfer easily to other number forms. So we're going to focus on this quotative conception. And we're going to read this as 8 divided into groups of 4. 8 divided into groups of 4. And when we do that, we can understand it as 8/4. Let's see how that plays out with something where the numbers are just a little bigger. 33 divided into groups of 7. I'm not going to draw 33 circles, but I know that I'm creating groups of 7. I know that each whole is going to be 1/7 of the group that I form. So this 33 divided into groups of 7 is going to be the same as 33/7. They're equivalent. Just like 8 divided into groups of 4 became 8/4, 33 divided into groups of 7, each whole is now 1/7 of that group of 7. Now, if we had to wrap our heads around how many wholes is that? Well, what do we know about sevenths? We know that 7/7 is 1 whole. Great. We could double that and get ourselves to 14/7. That's 2 wholes. We're getting closer to 33/7. That's how many we have. Well, if I double again, we have 28/7 for 4 wholes. That's not a bad place to start. 33/7 is equivalent to 28/7 and 5 more sevenths. 28/7 is 4 wholes. So 33 divided into groups of 7 is 4 and 5/7. Let's see again. 3 divided into groups of 3/4. Uh-oh. We have to divide into groups of 3/4. We have to divide into groups of 3/4. It'd be helpful if we had fourths. I've got 3 wholes, and I want to split it up into groups of 3/4. Well, let's check this out. Here's 3. And I'm drawing them a little bigger because I think if we're going to divide it into groups of 3/4, it'd be handy to have fourths. This 3, there's 1, 4/4. Another 1, 4/4. Another 1, 4/4. This is 1/4 of the whole. Now I have 3 wholes, and now I can split it up into groups of 3/4. Here's a group. There's a group of 3/4. There's a group of 3/4. Another group of 3/4. And another group of 3/4. We took the 3 wholes and we divided it up into groups of 3/4. When we took the 3 wholes and we considered it as fourths, this was 4/4, another 4/4, and another 4/4, for a total of 12/4. We conceived of 3 as 12/4. We substituted 12/4 for the 3. Now we're going to divide it up into these groups of 3/4, which really became 12. We had 12 of these fourths, and we divided it up into groups of 3/4. We had 12, and when we divided it up into groups of 3, there's 1 group, 2 groups, 3 groups, 4 groups. This apparently is equivalent to 12 divided into groups of 3. Because here, in this group, each one of these fourths, what was a fourth, is now 1/3 of the group. So we have these 12 divided into groups of 3 is equivalent to 12/3, as before, which is 4. Now, wait a second, you're saying. 12/4 divided into groups of 3/4 should be 4/4. What happened to the fourths? Where'd the fourths go? Okay, what if I had 12 x's, and I divided those 12 x's into groups of 3 x's? What if I had 12 x's and I divided them into groups of 3 x's? Well, how many groups would I have? Let's find out. So far there are 8 x's. we've got 12 x's. We want to divide them into groups of 3 x's. The question being, how many groups? Here's a group of 3 x's, another group of 3 x's, another group of 3 x's, another group of 3 x's. Notice each x is 1/3 of the group. We have 12 x's divided in groups of 3 x's. Here are the 3 x's. There are 4 groups. 4 groups. Also, each x is 1/3 of the group. So now we're counting thirds again. This is equivalent to 12 thirds, which is again 4. As long as the thing that we're counting is the same size, the answer we get is the number of groups that are formed, whether those are x's or quarters. 12 x's divided in groups of 3 x's is 12 thirds. Now, we could also build that a little deeper. 12 x's divided in groups of 3 x's could be 1 3xth, 1/3 of an xth. Well, this would be 12x divided into groups of 3x, or 12 of x of 1/3 of an xth. And multiplication is commutative and associative. So this is 12 of 1/3 of x of an xth. And as long as x isn't 0, this is 1 whole. So 12x divided in groups of 3x is just 12 thirds. Just like 12 fourths divided into groups of 3 fourths is just 12 thirds. It's the same understanding of division from whole numbers to fractions and to numbers expressed in standard decimal form. 5. I'm going to start by reading it. You're going to start by reading it. This says 5 divided into groups of 1 and 2/10. Don't throw yourself off by saying 1.2. You'll lose its value. 5 divided into groups of 1 and 2/10. I'm going to rewrite that, what I just said. This was 5 divided into groups of 1 and 2/10. This is a mixed number, 1 and 2/10. Well, 1 whole is 10/10. I have another 2/10. So this is 5 divided into groups of 12/10. Now, why would I do that? As before, I have 5 wholes divided in groups of 2/10. This is counting tenths. This is counting wholes. So it'd be easier to divide them into groups of 12/10 if this was expressed as a count of tenths. 5 wholes is equivalent to 50/10. 50/10 divided into groups of 12/10. 50/10 divided into groups of 12/10 is just 50 divided into groups of 12. We just proved this to ourselves with 12x divided in groups of 3x, that it's equivalent to 12 divided in groups of 3. We proved it. So this 50/10 divided in groups of 12/10 is 50 divided in groups of 12. Well, that's fun. You wished for a moment that this had been 6, so this could be 60, because 60 divides into groups of 12 a little easier. It's just not. That's not how it turned out. So we have 50 divided into groups of 12. Well, we don't have to think of it that way, right? With division, it's a multiplicative idea. I'm not going to draw 50 circles, but this is equivalent to 50 twelfths. Well, what do we know about twelfths? 12 twelfths, 1 whole. 4 times as much brings us to 48 twelfths. It's like I planned it. 48 twelfths, I'm close. We've got 48 twelfths. I can substitute that 50 for 48 and 2. I've got that many twelfths. 48 and 2 twelfths. That means we have 48 twelfths and 2 twelfths, which means we have 4 wholes and 2 twelfths. And we could have another conversation about how 2/12 is 1/6 if you want, but I want to focus on division right now. So let's either leave that as 2/12, or if you want to write it on your paper or your whiteboard as 1/6, go for it. But that's 4 and 2/12. That was 5 divided into groups of 1 and 2/10. Remember, numbers expressed in standard decimal form can also be rational numbers, which means they can be expressed as a ratio, which is a fraction. Can be expressed as a fraction. The two aren't different necessarily. Okay, where should we go next? We talked about whole numbers, fractions, numbers expressed in standard decimal form. I think it's time to think a little. We talked a little bit of algebra here. We should now deal with something like this. X and 3. Oh, it's expressed as a fraction already. This says the same thing as x and 3 divided into groups of x and 1. Typically, in an algebra course of study, it wouldn't be expressed this way. It would be expressed like this. But it's the same idea. This idea actually shows you how this quotative conception comes through, because this also is saying that we have x and 3 of these fractions. That we have x and 3 of those fractions. Well, and then the same question is the question, which is, do we have any wholes? And in fact, we do. Because how many of these fractions would we need to get one whole? Well, if we had x and 1 of those, we would have one whole. Of course. Side note, x can't be a det of 1. Because then this fraction would be 1 divided into groups of 0. A det of 1 and 1 is 0. 1 divided into groups of 0, it has no meaning. So, x and 1 of these fractions, x and 1/5, if you want, is one whole. We have that. We have x and 3. So we have x and 3, things got a little messy here, but x and 3 could be substituted for x and 1 and 2 more of these fractions, which means we have x and 1 of them and 2 more of them, which means we have one whole and 2 of those fractions. Same understanding of division, it's growing into algebra for us. Now, I'm going to do like a long view learner and draw ourselves a little line to differentiate one question from the next. Quadratic divided by a linear expression. We don't need long division for this. You might think we do. We don't. We can use the same understanding, because what are we counting? We have k squared and 5k and 7. We have that quantity divided into groups of k and 2. What do we know about this fraction? Right? This means we're going to be counting that fraction. We have this many of these. We have this many of these. We can reason with this. We don't just have to follow a procedure. We can reason with it. We know that this is one whole as long as k is not a det of 2. Else, things don't work. But k and 2 of these k and 2/5 is one whole. Okay, well, if that's one whole, let's try something. We've got, if I wanted k of them, I would need k. If I wanted k, I would have k times as many, so I need k of these. I would need k of these and I'm writing it this way because I want you to see that we've got k of these fractions, which means we have k of k and 2 of that fraction. That's what this is equivalent to. This, if we distribute, is k squared and 2k of those fractions, of those k and 2/5. We have k squared and 5k and 7. That means we have k squared and 2k. We have that. We have that. And we have 3 more k's, and we have 7. And we can distribute. We have that, and we have this. And we just said that this fraction that this fraction equals k. This first term in this expression is k. And 3k and 7 of the k and 2's. Well, if k times as much brought us here, we could also start with this whole, this k and 2 of a k and 2th equaling 1. We could have 3 wholes. What would 3 wholes be? It would be 3 of these. 3 ones would be equivalent to 3 of these. So if we had 3 of those, that would equal 3. Now, why did I pick 3? Because of this 3k. That 3k told me I wanted a 3k. That's why I went hunting for 3. Truth is, that's why I first thought of that, why you could also think of starting with k, because we had this k squared. See, I knew that you knew that k squared is k of k. So 3k and 2 of those is 3k and 6 of those fractions. Well, we have 3k and 7 of them. That means we have the 3k and 6 of them, and 1 more of them. That means we have k and 3 and 1 of these. Same understanding of division. Whole numbers, fractions, decimals, algebraic expressions, this quotative understanding of division where we can count a fraction transfers all the way through.